I want to do two examples factoring higher degree polynomials using synthetic division. And in this case, we're going to look at examples that may not have all rational zeros, so we can see how to handle that. Also, how to handle a leading coefficient other than 1. So let's get into the first example. Let's try to factor. Let's say this first example is a cubic polynomial. So factor 4x to the third plus 4x squared plus 3x plus 1. And so when you look at this and you see four terms, you might think to try factoring by grouping, and I encourage you to do so. But factoring by grouping won't work because you're not going to be able to make the first group and the second group look the same after factoring out a common factor. So we need something else. And the other option we have, if we can't factor it using our traditional techniques, is to search for rational zeros. And so since this is degree 3, excuse me, and we want to reduce it to degree 2 so that we can use the quadratic formula or some other quadratic technique, we need to find one rational zero using synthetic division. Okay, so let's list possible rational zeros so that we can start testing them until hopefully we find one. So the possible numerators of our rational zeros are factors of the constant 1, and luckily for us, 1 is its only factor. So the numerator has to be plus or minus 1, and the denominator has to be factors of the leading coefficient 4. So those are plus or minus 1, 2, and 4. So let's make our list of possible rational zeros by pairing every numerator with every denominator. So I could have plus or minus 1 on top with 1 on bottom, which is 1. I could have plus or minus 1 on top with 2 on bottom, so that's 1/2. And I get a plus or minus 1 on top with 4 on bottom. So I've got 6 possible rational zeros here. And I want to start testing. And I don't necessarily need to test all of them. I just need to test until I find one that works. So let's test 1 first using synthetic division. So I'm dividing 4x cubed plus 4x squared plus 3x plus 1. There are no missing terms here, so I don't need any zero placeholders in my synthetic division. So my coefficients are 4, 4, 3, and 1. Drop your 4 down, multiply and add. Multiply, add, multiply, and add. And we don't get a remainder of 0. So 1 is not a 0. Let's test negative 1. 4, 4, 3, 1. Drop the 4 down, multiply, add, multiply, add, multiply, and add. And we don't get a remainder of 0 there either, so negative 1 is not a rational zero. Let's test 1/2. 4, 4, 3, 1. Drop the 4 down, multiply, add, multiply, add, multiply, and add. We don't get a remainder of 0 there either. So far we've tested 3 out of our 6 possible rational zeros. Let's test negative 1/2. 4, 4, 3, 1. Drop the 4 down, multiply, add, multiply, add, multiply, and add. And there we go. Negative 1/2 is a 0. All right, so we found our one rational zero, and now since we've divided, the result should be degree 2. So if we look at the quotient here, right? We started with an x cubed polynomial, and when we divide, we get an x squared polynomial, 4x squared plus 2x plus 2. So we need to solve the equation 4x squared plus 2x plus 2 equals 0, and we can do that using the quadratic formula since this is degree 2. Now you could use 4, 2, and 2 as your a, b, and c values, but I noticed that all three of those terms are divisible by 2. So I'm going to divide both sides by 2 to make all the numbers smaller, and notice that doesn't change the 0 on the right. But on the left, I get smaller numbers. So A is 2, B is 1, and C is 1. So now we can plug them into the quadratic formula to find our last two zeros. So x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Now we just need to simplify. We get negative 1 plus or minus the square root. 1 squared is 1 minus 4 times 2 times 1 is 8. And that's all over 2 times 2, which is 4. So finally we get negative 1 plus or minus the square root of 1 minus 8 is negative 7 over 4. And last but not least, we need to take the negative out of the square root because this is an imaginary number and turn it into an I. Make sure you put the I right in front of the square root, not in front of the plus or minus, all over 4. And so these are also zeros, okay? So we got negative 1/2 as a 0, and we got 2 more zeros here. Now we need to turn those into factors because our goal here was to factor the polynomial. Now let me copy the original polynomial down again. 4x cubed plus 4x squared plus 3x plus 1 equals, right? When you factor, you're just writing a factored version of the polynomial. So negative 1/2 was a 0. If I want to turn it into a factor, I have to do x minus negative 1/2, which is the same thing as x plus 1/2. Then I need x minus each of these complex zeros. So I'll have x minus negative 1 plus I square root 7 over 4. And then I'll have x minus negative 1 minus I square root 7 over 4. And so now I've factored this polynomial, or so it seems. At least I found the zeros and turned each zero into a factor using x minus that 0. However, you might notice that these two things are supposed to be equal. These two expressions are supposed to be equal. And if I multiply out what I have on the right side, if I multiply all of this out, well, my first term is going to be x times x times x, which is just x cubed. And I need my first term to be 4x cubed if these two expressions are truly going to be equal. The good news is that's easy to adjust. All I have to do is put a coefficient of 4 on the front, multiply this entire expression by 4, controlling my leading term. Because now if I multiply out the right side, I get 4x cubed as my leading term. Thus, this is the proper way to factor the polynomial. You always need to watch for that leading term and matching its coefficient, okay? Let's try another one, but let's do a degree 4 polynomial instead. So let's factor 3x to the 4th plus 16x to the 3rd minus 11x plus 2. Grouping won't work again, so let's look at the degree, which is degree 4. If I want to reduce it to a degree 2, which is always our goal, because degree 2 allows us to use quadratic techniques. This is degree 4, so I need I need 2 rational zeros. Okay, so now when we're testing from our list, I need 2 numbers from the list to work. So let's list all the possible rational zeros. The numerators will be the factors of the constant 2. So I've got plus or minus 1 and 2. The denominators are going to be, the possible denominators are the factors of 3, which are plus or minus 1 and 3. So now I need to list all the fractions that could be made up of these combinations. So I could have plus or minus 1 on top with a 1 on bottom, plus or minus 2 on top with a 1 on bottom, plus or minus 1 on top with a 3 on the bottom, and last, plus or minus 2 on top with a 3 on the bottom. Okay? So let's get started with our testing. So let's test 1 first. I always like to test the whole numbers first. There's no particular order that you need to test these. Just make sure that if you test something and it doesn't work, you never test it again, because it will never work. All right, so 1. If I test 1, I need to plug in my coefficients of 3x to the 4th plus 16x cubed minus 11x plus 2. We can see that this polynomial is missing an x squared term, so it's going to need a 0 placeholder for the x squared part. So we've got 3x to the 4th, positive 16x cubed, 0x squared, negative 11x, positive 2. Okay? Now we can start testing. Or start the synthetic division. Drop the 3 down, multiply, add, multiply, add, multiply, add, multiply, and add. We do not get a remainder of 0, so 1 is not a 0 and it never will be. Let's test negative 1. 3, 16, 0, negative 11, 2. Drop your 3, multiply and add, multiply, oops, that's positive 13, and add, multiply, let me see, did I copy something wrong here? 3, negative 3, 13. Okay, yes, sorry, that is negative 13, because negative 1 times positive 13 is negative 13. Then I add 0 plus negative 13 is negative 13. Then I multiply and get positive 13, and I add and get positive 2, multiply and get negative 2, add and get 0. So negative 1 is a 0, and now we continue the process because we need 2 rational zeros, but when we continue the process, we continue on this new quotient. We don't go back to the original polynomial. That's usually where students make their mistake. The other thing is when you find a 0 that works, you need to test it again because it could work more than once. Negative 1 could be a 0 2 times. So let's go ahead and just use what we have here. Let me get rid of that green highlighting. Hopefully I can. Yep. So now I'm just using negative 1 again with 3, 13, negative 13, and 2. So drop the 3 down, multiply, add, multiply, add, multiply, and add. So now we don't get a remainder of 0. Therefore, negative 1 is not a 0 again. I don't have to ever test it again. So let's continue through our list. I've tested 1 and negative 1. Let's test 2. In the interest of time, I'm going to tell you that 2 does not work. Then let's see, test negative 2. Negative 2 does not work. Then let's test 1/3, which also does not work. Negative 1/3 does not work. Let's see here, positive 2/3. Let's test that one. Again, if you're doing this on your own, there's not really a good way to pick an order of these. So you just have to kind of run through the process. On a test or something, you would hope that this list would be shorter, or maybe you see how you need 2 rational zeros. Maybe one of them would be provided for you so that you only had to figure out the other one. Anyway, lots of ways to make these problems quicker on the instructor side of things. Nonetheless, even if the list is long, you could eventually figure it out. All right, so let's test 2/3. And remember, we're working on this quotient now, not the original polynomial, okay? So I'm going to put in 3, 13, negative 13, and 2. Drop your 3. 2/3 times 3 is 2. 13 plus 2 is 15. 2/3 times 15 is 10. Negative 13 plus 10 is negative 3. 2/3 times negative 3 is negative 2. And 2 plus negative 2 is 0. So 2/3 is our other rational 0. So we've got our two rational zeros that we were looking for. Thus, the resulting quotient here should be degree 2, and it is, because remember this was degree 4. When we divided, we got degree 3, which is what we had here. And when we divided again, we've got degree 2. So now we need the zeros of 3x squared plus 15x minus 3. Again, we can divide both sides by 3 to make all the numbers smaller. X squared plus 5x minus 1 equals 0. And now we can use the quadratic formula to find the last two zeros, giving us 4 zeros altogether. So A is 1, B is 5, C is negative 1. So we get x equals negative b plus or minus the square root of b squared minus 4 times a times c. And that's all over 2 times a. Since I'm limited on real estate, I'm going to work horizontally here, which is typically bad practice, but it's going to be easier for you to see everything. So I've got negative 5 plus or minus the square root. 5 squared is 25. 4 times 1 times negative 4 is negative 4. I've got minus negative 4, so that turns into plus positive 4 over 2 times 1, which is 2. So I get negative 5 plus or minus the square root of 29 over 2. And I can't split the square root of 29 at all, so those are my last two zeros. Okay, so we have 4 zeros. Negative 1, 2/3, and these two irrational zeros in fraction form. And our goal here was to factor this polynomial. So let me write out the polynomial again. 3x to the 4th plus 16x to the 3rd minus 11x plus 2 equals, and then I'm going to turn each of the zeros we found into factors by doing x minus. So the first zero we found was negative 1, and if we do x minus negative 1, that's the same thing as x plus 1. The next zero was 2/3, so I need to do x minus 2/3. And then we have two zeros here. One of them is negative 5 plus the square root of 29 all over 2, so I need to do x minus that. And the other is negative 5 minus the square root of 29 all over 2, so I need to do x minus that. And now the two expressions on the left and right need to be equal, so I need to look into making sure that my leading coefficient, my leading term is 3x to the 4th. And if I multiply all the leading terms together, I would just get x to the 4th. So to fix that, I just build in a coefficient of 3 on the right side, and then I'll get a coefficient of 3, thus making the two expressions equal. And now we factored this sort of difficult degree 4 polynomial using synthetic division with some rational zeros and some irrational zeros, as we see there, verifying that we even get the leading term correct by building in the right coefficient.